Hey, how are you guys doing? We are going to start our unit today talking about freezing point depression and boiling point elevation. These are two of what we call colligative properties or properties of solution. So moving on, basically what happens when you mix a solute into a solvent is that it changes both the freezing point and the boiling point of the solution. Um, in the case of a freezing point, the freezing point of the solvent is made lower, and its boiling point is raised whenever you add a solute. And that's just because the solute is in there basically interfering with all of the interactions between the solvent molecules, which can prevent them from forming a solid in the case of freezing, but also prevent them from being able to escape through evaporation and really get to the gas stage, which is what boiling is. So just the presence of the solvent interferes with those processes, lowering the freezing point and raising the boiling point. And so this brings us to a couple of things that we can actually calculate. We can calculate the change in freezing temperature, which is just the difference of the freezing point. That's what FP stands for, freezing point. And so we can change that freezing point of a solution and find the freezing point of the solvent compared to that solution. And that is our change, our delta temperature freezing, right? Remember the triangle is a delta and it just means change. So change in temperature in this case. And the change in boiling point, similarly, is the difference between the boiling point, BP, of a solution and the boiling point of that pure solvent. And there are equations that relate the concentration of the solution to how much that temperature is changed. And that's what we're going to look at in our next slide. So basically, there's a constant that relates how the molality, remember, is the moles of solute over kilograms of solvent. It's one of our measurements of concentration. And it is proportionate to the change in freezing point of the solution. So how much the freezing point temperature changes is proportionate to the molality. And you multiply that by some constant. Now, this constant is what we call the molal freezing point depression constant, or K sub F, and it depends on the solvent. But its units are always going to be in degrees Celsius per molal, and it will be given to you in problems. So, I'll tell you the KF of water or the KF of whatever solvent we're using in that particular problem. So it's a number that will be given to you. So this is really easy math because essentially we're going to take the number that's given to us in the problem, we're going to figure out the molality of the solution, and then that will give us the change in freezing point. So we can add or subtract it as appropriate. In this case, because freezing point is going to be lowered, we would subtract the difference of the freezing point. Similarly, there is an equation for how much the temperature of the boiling point changes. And it's basically the same equation, except it's KB instead of KF. So this is going to be the constant of boiling point elevation, or the molal boiling point elevation constant. It's also expressed as this equation. It's also a proportionate equation. So the change in boiling point is equal to the constant times the molality of the solution. And again, like we saw before, that constant depends on the solvent. Units are still the same, degrees Celsius per molal, and we will give that to you in any questions. So you don't have to figure that out. It'll just be given to you in the equation. Although I could give you an equation where I told you the change in boiling point and the molality, and then you have to figure out the constant. But you'll always have two of the three pieces of information, right? Just missing one thing that you have to look for. So let's go ahead and jump into a problem, right? So here's an example. What is the freezing point depression and boiling point elevation? So we're going to do two different problems here, really, of an aqueous solution of 10 grams of glucose, which is C6H12O6, in 50 grams of water. So we'll take a look at how to solve this. So first, of course, we have to check our givens and make sure that they're in the right units and everything, and look at our equation. So we're looking at calculating both the freezing point depression and the boiling point elevation of an aqueous solution of 10 grams of glucose in 50 grams of H2O. So we're going to look at our equation first for freezing point. The delta T of freezing, or the change in temperature of the freezing point, is equal to the constant of freezing times the molality of the solution. And so we have to have the molality and the constant of freezing. We have our constant of freezing. We don't have our molality, but we have enough information to figure it out. We know the amount of solute and we know the amount of solvent. And remember, our molality is going to be equal to moles of solute over kilograms of solvent. So we have to convert some of our units. First, we need to take our grams of glucose and turn it into moles. So for that, we need the molar mass. So we know that the equation for glucose, the formula is C6H12O6. So that means when we go to calculate our molar mass, we're going to have 6 times 12.01 plus 12 times 1.008 plus 6 times 16, really 0.00, but it's just 16. And that all comes out to 180.156, which we, of course, round to 4 significant digits, so 180.2 grams per mole is going to be our molar mass. And so then we can convert our 10 grams of glucose, C6H12O6, using our train tracks. 180.2 grams is 1 mole. And then we can get our answer because our grams are canceled and we're left in moles, and that came out to be 0.056 moles, or 0.0555, which rounded to 0.056 moles of glucose. And then we need to convert our grams of H2O into kilograms. So we have 50 grams, and we need to convert that into kilograms. Well, 1 kilogram is 1,000 grams, so our grams cancel, and we come out with 0.05 kilograms. So when we put that together to calculate our molality is moles of solute over kilograms of solvent. So that's going to give us 0.056 over 0.05 for our molality, and that equals 1.11 molal solution. So now we've got our molal solution, we have our molality, and we already know our constant of freezing is 1.86. So we can now really easily calculate the difference in freezing point. The difference in temperature of the freezing point is going to be 1.86 times our 1.11, which we got from calculating our molality. And when I got all that together, I got 2.06 degrees Celsius is going to be our freezing point depression. Now, because we know that when we add a solvent or a solute to a solvent, that it's going to lower the freezing point, I'm just going to put a negative here to remind myself that that is going to depress the freezing point. It's going to go down. So if I wanted to know what the final freezing point of that solution would be, I would take the freezing point of the solvent, which I know is water, and I would subtract the 2.06, right, which would give us a freezing point of negative 2.06 degrees Celsius. And so that gives us our freezing point depression and our new freezing point of the solution, but we still have to answer the rest of the question, which is and boiling point elevation, right? So for that, we need basically the same information. If we look at the equation, it's going to be the delta temperature, the change in temperature of boiling, is equal to the constant of boiling this time, not the constant of freezing, times the molality of the solution, right? Because it's based on concentration, because how concentrated the solution is affects how much disrupted the temperature of the boiling point is going to be. So we've already calculated the molality. We've already done all of our unit conversions. We know our constant of boiling is 0.52, so it's going to be really easy to figure this out. We just have to sub everything in, so that's going to be equal to 0.52 times 1.11. And when we work that out, we get 0.577. Now, because it's boiling point elevation, and we know that elevation is raising of the boiling point, that number is going to stay positive. And if I were to ask you what the new boiling point would be, well, we know that in Celsius, the boiling point of water is 100. So we would just add that to 100. So we would just say plus 100, giving us a new boiling point of 100.58 probably degrees Celsius. So not raising a whole lot, definitely dropping the temperature more than for freezing than it is raising for boiling. But that's how you work out these problems. The hardest part is making sure that everything is in the right units so that you can calculate your molality, which is what we practiced in the last class. So now you should go on and work the next problem on your own. Turn off the video, work your problem, and then you can come back and check. I'll do my work on the video next, and then we'll move on to some other questions. All right.